Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to go over an exercise where we're going to try to find indefinite integrals involving the powers of tan and secant. Okay, we had a similar version of that earlier for the integrals involving the powers of sine and cosine, and we had a good recipe for that. And we are going to have a similar recipe for handling these integrals. And before I get started with part A, I'm going to show you those guidelines, and let's just sort of like go over them real quick. All right, here they are. So we have different kinds of integrals involving secant and tan. If you look at the first one, we're specifically talking about secant raised to an even power. When you see a situation like that, you're going to save 1 secant squared x for dx, and with the leftover powers of secant, so you're going to write that term as like secant squared raised to whatever the power it corresponds to, and you use the known Pythagorean theorem that secant squared equals 1 plus tan squared, and starting from there you can start calling u to be tangent x, and this problem turns out to be a u substitution problem. And in another scenario, you have secant against tan, but tan is raised to an odd power. In that case, you're going to reserve not just tan, but secant as well for dx. So secant tan is reserved for dx. With the leftover terms, you have tan squared raised to a power of k in this case. So I'm going to play with tan squared by using the Pythagorean identity. So I replace that by secant squared minus 1. And at this moment, the reason why we had secant x, tan x reserved for dx is just because I'm going to use u substitution where u is secant x. How nice, because du is secant x tangent x dx, so that's exactly what we reserved for dx, okay? So let me just show you a few more. So here, if you have the powers of tan only, so what you're going to do, if that works, you're going to reserve tan squared x for dx, but not necessarily for dx, so you are supposed to replace tan squared by secant squared minus 1, and you're going to use, if applicable, u substitution. In the fourth case, we have secant raised to an odd power, and this is an application of integration by parts, so apply integration by parts, okay? When the first 4, in fact, guidelines do not apply, it says 5, but it's 4, okay? Then try converting to sines and cosines. So if you're given like tan and secant all together, use the definition of tan, which is sine over cosine, and secant, which is 1 over cosine, to simplify the integral, and then maybe you can go back to the guidelines for integrals involving sine and cosine, okay? So you must have the copies of that in your ebook. Please have it somewhere, because I'm going to refer back to those guidelines in the video. All right, let's get started. All right, let's start with part A. I have tan cubed and I have secant squared. So we can go back to the guidelines and check if there is anything fitting in this form. We have tan cubed, so tan comes with an odd power. That does sound like number 2 is a good fit for that. But in the meantime, secant comes with even power. Here we go. Number 1 also fits in what we have. But I feel like these two items are sort of overkilling, because if you go back to what we have in the question statement, I have tan cubed secant squared, and I have tan having the derivative of secant squared. So that means if I call u to be tan pi x over 2, I can convert this integral into something very simple in one shot. So u substitution, just one u substitution would be more than enough to convert this integral to something that we know how to integrate. Okay, so what I'm trying to say is I'm going to call u to be tan pi x over 2, so that when I take the derivative of that, okay, it's going to be pi over 2 secant squared pi x over 2. That's me using the chain rule. Okay, The outer function is tan, having the derivative secant squared. The inner function is pi over 2x, having the derivative pi over 2. So that's a quick application of the chain rule, okay? All right, then I can rewrite this integral as, well, first of all, secant squared pi x over 2 dx is 2 over pi du. Okay, that's first thing, okay, to do, 2 over pi. And I have u cubed here. So that means I can pull out 2 over pi because it's a constant. And I can write this as like u cubed du. See, in one u substitution, with one u substitution, we were able to convert this integral to something really easy to integrate because we only need to use the power rule for integration here. So this is 2 over pi u to the fourth divided by 4 plus c. Let's simplify this even further and put the u back. So u to the fourth over 2 pi plus c. So tan, or 1 over 2 pi, tan pi x over 2 to the power of 4 plus c would be the final value of this indefinite integral. So this was an example where you did not need to use the guidelines for integrals involving powers of secant and tangent. This doesn't mean that you can't apply those. You can still apply those, but these two items would make this solution a little bit longer. But you can pause the video anytime, and then, in fact, I'm going to finish this video right now for part A. But at the end of this video, you can try one of those items to see if they are applicable and if you get something easy to integrate at the end. Okay. So I'm going to finish this video right now, move on to part B in the next video. I'll see you there. Bye.